This lecture is devoted to moving from transfer functions to their state space realization and to making the correspondence between certain transfer function representations and the corresponding state space representations. So what we will begin with is a transfer function which we will call h of s, and we want to go from that transfer function to a state space representation x dot equals ax plus bu, y is equal to cx plus du. There are several ways of doing that, and for all practical purposes I just want to show you some examples. Let us begin with the transfer function 1 over s plus 1. Such a transfer function is easy because we can write that y hat over u hat is equal to 1 over s plus 1, or y dot plus y is equal to u. As a result, the transfer function the state space realization can be expressed by saying that x is equal to y, x dot is equal to minus x plus u, y is equal to x. Now let's look at another transfer function, 1 over s plus 1 squared. So this is slightly more complex, but we can build it from here. Indeed, if our input u is here, we pass it through a first transfer function 1 over s plus 1. We then pass it through a second transfer function 1 over s plus 1, and we get y at the output. From what we have said here, we can define a state space representation x1 dot is equal to minus x1 plus u, and then the output v would be x1. Second, we have x2 dot is equal to minus x2 plus v, and y is equal to x2. If we concatenate these two and write x is equal to x1, x2, we can write that x dot will be equal to minus 1, 0, minus 1, and then 0 is equal, v is equal to x1. So something like this times x plus 1, 0 times u, and y is equal to 0, 1 times x. We see that we can do this for 1 over s plus 1 to the power p, where p is arbitrary. And what we see is that if I simplify all this, let me erase this, we can write that the corresponding realization will be x dot is equal to minus 1, minus 1, minus 1, minus 1 p times, with the ones under the diagonal and zeros everywhere, times x plus 1, 0, 0 times u, and y is equal to 0, 0 times x. My mistake, we need to have a 1 at the end, otherwise we'll read nothing. Now, I would like to bring an alternative representation. Indeed, what we can do is, let me go here, and let me do this again. What we can do is, if we take 1 over s plus 1 squared, we can also rewrite this as 1 over s squared plus 2s plus 1. Under which condition we can write that y hat over u hat is equal to 1 over s squared plus 2s plus 1, or in other terms, y double dot plus 2y dot plus y is equal to u. That other differential equation can be written with the state xi is equal to y dot as satisfying xi dot is equal to 0, 1, and then minus 1, minus 2 times xi plus 0, 1 times u, and y is simply equal to 1, 0 times xi. Notice that this representation here is different from that representation there. However, the two representations are completely equivalent, and therefore there is a state variable change that transforms this one, A matrix, to that one, A matrix, this one, B matrix, into that one, B matrix, this one, C matrix, into that one, C matrix. Therefore, for the same transfer function, you can very easily find two different state space representations. Let's explore this idea a little more. We're going to look at the following. If I erase my entire worksheet, I can introduce a new system, which I will call 1 over s plus 1 times s plus 2. I can think of this thing in several ways. First, I can write this as it is, the mounting in series of 1 over s plus 1 and 1 over s plus 2, these two transfer functions, and as follows. The input is u, the output is y. Now I can also think of it as 1 over s squared plus 3s plus 2, in which case it looks like the single transfer function u is equal, the simple transfer function, which I will write as 1 over s squared plus 3s plus 2. Out of which comes y. Last, I can also think of it as a over s plus 1 plus b over s plus 2. Now, we can easily compute that a will be equal to 1 and b is equal to minus 1. Indeed, s plus 2 minus s minus 1 is 1. Let me replace a and b by their value. One here and minus 1 there. And I can say that this, since this is the sum of two transfer functions, I can represent the system as u split into feeding two boxes. One will be 1 over s plus 1. The other would be minus 1 over s plus 2. And the two output merge to produce y. Okay? They merge by summing up. So the output is y, the input is u. Now, this leads us to the state space representation. A equals minus 1, 0, 1, minus 2. B is equal to 1, 0, and C is equal to 0, 1. As we have seen in the previous page. Now this one naturally leads leads itself to A tilde is equal to 0, 1, and then -2, -3, and B is equal to 0, 1. I put a tilde to differentiate it from the previous one, and C tilde is equal to 1, 0. Now, in the third representation, we have that we have the realization of two separate systems which we haven't seen yet. Okay, x1 dot is equal to minus x1 plus u, x2 dot is equal to minus x2 plus u, and therefore x dot is equal to minus 1. Sorry, this is not minus, it's minus 2x2. Okay, let me correct this. Minus 2x2 times x plus 1, 1 times u, and y is equal to the sum of these two. Therefore, y is equal to 1, 1 times x. These three realizations, or these three state space representation of the system, are different, yet totally equivalent. In particular, we can go from any of these representations by means of some transfer or some matrix P. That means we have a certain P such that P A tilde P inverse is equal to A, and such that C tilde times P is equal to C, and P inverse times B tilde is equal to B, just like what we have seen in the previous lecture. The same holds between this matrix A and that matrix A. However, the change of coordinates will be different. Let me discuss now shortly the advantages and disadvantages of all these representations. It is not very clear as to whether there is an advantage comparing this transfer function and the corresponding state space representation, and that transfer function and the corresponding state space representation. However, here we can see an obvious advantage. Indeed, these two systems run in parallel, and therefore they can be understood as two independent systems, or one so-called diagonal system here. Simulating these systems separately is much cheaper than simulating a 2x2 matrix here. And in fact, we can find closed form formulas for this and that differential equation, these closed form formula are not extremely complicated. In comparison, finding closed form formulas for this one represents a little bit more of an effort, and therefore may not be as interesting. So what we can do now is move on and talk about other transfer functions, especially the ones with s's on top. So what we are facing are transfer functions of the following kind. For example, s divided by s squared plus 2s plus 3. Or, for the sake of convenience, I'm going to say minus 3. So if this is my h of s, how do I write the corresponding state space representation? I can write that y hat over u hat is equal to s divided by s squared plus 2s minus 3, which I can also write as y double dot plus 2y dot minus 3y is equal to u dot. Now, this is a little bit annoying for the following reason. We don't feel like we need u dot. Our input is u, not u dot. So, to help with this, we have a number of possible options. One of them is to go to a partial fraction expansion. S divided by s squared plus 2s minus 3 will be equal to a over s minus 1. Indeed, 1 is a root of that system, plus b over s plus 3. We obtain that a times s plus 3 is equal plus b times s minus 1 must be equal to s. Or in other terms, a plus b is equal to 1, and 3a minus b must be equal to 0. We get that b is equal to 3a, or a is equal to 1/4, and b is equal to 3/4. Yielding, once we have replaced a and b by their values, the partial fraction expansion to be like this. Now these are two parallel systems which I can once again write as follows. We have the input u, it splits and feeds into two independent systems. 1/4 divided by s minus 1 on the one hand, and 3/4 times 1 over s plus 3 on the other hand. The outputs of these two simple systems sum up to produce y. Under this case, an easy transfer function, state space representation would be x dot is equal to 1, 0, 0 minus 3 times x plus 1/4, 3/4 times u, and y is equal to 1, 1 times x. This is fine, and we see that we don't need indeed u dot in order to find a state space representation of this transfer function. So again, we need to ask ourselves, what is going on here? But as we think about that, we go back here and we realize that this is a perfectly valid state space representation. Another state space representation would work as follows. I can write that s over s squared plus 2s minus 3 is equal to s over s minus 1 times 1 over s plus 3. For that, I can rewrite this as 1 plus 1 over s minus 1 times 1 over s plus 3. Let me eliminate this transfer function and instead try and find what this guy looks like. Well, it looks like two boxes mounted in series. By the way, since they commute, I can first begin with 1 over s plus 3 and then go on to talk about 1 plus 1 over s minus 1. U enters here, y exits there. So what happens? Well, this guy has an obvious state space representation. x1 dot is equal to u minus 3x1. This one has a state space representation which is the sum of this term and this term. This term is a fit-through term. This term is a regular term. You can easily check that it's a state space state space representation will be x2 dot equal x2. Oh, I'm going to call this variable v, so it's going to be x2 plus v. And then y is equal to x2 plus v, because there is a direct fit-through term. Y is equal to 1 times v plus this transfer function. And therefore, when I mix all these and I add that v is equal to x1, I obtain the following differential equation: d dt of x1 x2 will be equal to -3 0 times x1 x2 and then x2 plus v, which is x1, plus b, and the B matrix will just be 1, 0 times u. Y being equal to x2 plus v, or x1 plus x2, therefore 1, 1 times x1, x2. Therefore, once again, a representation of the system where only u and not its derivative does appear. We now go back to our original problem, and our original problem was this equation and finding a proper differential equation representation for it. So what I'm going to do is try a simplification and a change of viewpoint. We have seen that the transfer functions, there exists transfer functions, or to be more precise, state space realizations, state space representations of the systems that don't show u in it. My mistake, that don't show u dot in it. So let me define the following. I'm going to first integrate this equation once. Another way of saying it is that if my initial equation was s squared times y plus 2s times y minus 3y is equal to s times u, I'm going to divide everything by s, and I'm going to call z is equal to y over s. What do I obtain? This, once I multiply by 1 over s, here and there, if I define z is equal to y over s, I will obtain the corresponding equation. S times square times z plus 2s times z minus 3z is equal to u. Or, in other terms, we can write that z double dot plus 2z dot minus 3z is equal to u. Now, if y is equal to z times s, that means y is equal to z dot. As a state space representation for this, we can, choosing x is equal to z dot, we can write that dt of x will be equal to 0, 1, and then 3 minus 2. My mistake. Times x plus 0, 1 times u. Since y is equal to z dot, we get that the y is equal to 0, 1 times x. Very good. So what that gives us is yet another state space representation of that system. Therefore, you should not be afraid of the presence of s's or powers of s on the numerator. Thank you.